Hello everyone, I am Om Krishna Gupta. I am assistant professor in Electronics and Communication Engineering department in Ajay Kumar Garg Engineering College, Ghaziabad. This is lecture 21 of the subject analog circuits. In this class, I am going to discuss different types of current mirrors. Contents are current mirror with base current compensation, Widlar current source, and after that Wilson current mirror and Cascode current mirror. So, before this class I had discussed what is current mirror, what are the different properties of current mirror, what are the desirable properties of current mirror, and I had discussed in the last lecture about the basic current mirror using BJT, using MOSFET, and what are the issues in basic current mirror, and what are the factors which affect the performance of the current mirror, and after that I had discussed current repeaters. So, before I start the first current mirror, that is current mirror with base current compensation, let us quickly review about current mirror. So, basically current mirror, it is a circuit which just copy the input current. So, in the current mirror, the input current is equal to output current. It is called mirror because the output current is the mirror of the input current. So, such kind of circuits are used to bias the amplifier in biasing, and also we can use current mirror as an active load, because this current mirror is made up of transistor, either BJT or MOSFET. So, these are the main uses of the current mirror. Fine. So, starting with the first kind of current mirror, that is the base current compensation current mirror, and of course, for any current mirror, two important factors are there. The first factor is the output resistance. The output resistance, ideally it should be infinite, practically obviously it should be very high, output resistance should be high and the input resistance should be low for any current mirror. And also the current transfer ratio CTR, current transfer ratio, it should be 1. If the current transfer ratio is 1, it means that the input current is equal to output current. Also we can amplify the input current depending upon the W by L ratio of the output transistor that I had discussed in the last class, but when we want the same current at the output side, then what we need? The current transfer ratio should be 1. So, this circuit is the current mirror with base current compensation. If you compare this base current compensation current mirror with the basic current mirror, then you can see that there is an additional transistor Q3 whose base is connected to the collector of Q1 and the emitter is connected to the base of Q1 and Q2. In the basic current mirror, there is no Q3, and in current mirror circuit, the base voltage of both the transistors Q1 and Q2 and the emitter voltage of both the transistor Q1 and Q2, it should be same. That is why base of Q1 and Q2 are shorted, emitter of Q1 and Q2 are shorted. In case of MOSFET, the gate should be shorted and the source should be shorted. And in the basic current mirror, this Q1, it acts as a diode connected transistor, right. That is why base is directly connected to that collector, but here there is an additional transistor Q3. Now, we will understand that when we connect this Q3 transistor in the basic current mirror, then what happens, how it improves the performance of the basic current mirror. For that, let us first derive the relation between the output current and input current. Output current is I naught and input current, that is the reference current, that is I reference. Now, to find out the relation between I reference and I naught, apply KCL at this node X. apply KCL at node X, then what we will get? I reference incoming current is equal to output incoming current is equal to outgoing current. I reference is equal to IC plus the base current of the Q3 transistor. Now, what will be the base current of Q3 transistor? We can understand it. The base current of Q1 transistor, it will be IC upon beta. If the collector current is IC, then the base current will be IC by beta, because the relation between the collector current and the base current is IC is equal to beta IB. So, the base current of Q1 is IC by beta, and base current of Q2 is also it is IC by beta, right, if Q1 and Q2 are matched transistor. And of course, in current mirror we take matched transistors. Matched transistors means the beta of both the transistors, it will be same, fine. So, from the circuit you can see that what will be the emitter current of Q3? It will be 2 IC upon beta, that is dividing into two parts, IC by beta of for Q1 transistor and IC by beta for the base current of Q2 transistor, fine. And if we know the emitter current of the transistor, then we know the relation between the base current and the emitter current. The base current is emitter current upon beta plus 1, or we can say that emitter current is equal to beta plus 1 times the base current. So, if the emitter current of Q3 transistor is 2 IC by beta, then what will be the base current? It will be the emitter current upon the factor this beta plus 1. So, when we apply KCL at node X, then we can write it as I reference is equal to IC plus it is 2 IC upon beta plus 1, fine. Now, we can take IC common, then we will get this expression, and of course, since this is a current mirror, I naught is equal to IC. So, what will be the value of I naught upon I reference? Let us say it is equation A. So, from equation A we can find out the value of I naught upon I reference, fine. So, I naught upon I reference, it is 1 upon 1 plus 2 upon, now beta into beta plus 1, if we multiply beta inside the bracket, it is beta square plus beta, and since beta is very large, beta of the transistor is very large. So, we can say that we can consider it beta square is very greater than beta, because beta is very large. So, we can neglect this beta square factor, not beta square factor, beta factor, fine, because beta square is very greater than beta. So, I naught upon I reference, it will be 1 upon 1 plus 2 by beta square. This is the relation between output current and input current. Now, you can compare this equation with the equation of the basic current mirror. In the basic current mirror using BJT, what we had got in the last class, that expression is 1 upon 1 plus 2 by beta, but here we are getting 1 upon 1 plus 2 by beta square. So, which one is better? What we want? We want that the output current should be exactly equal to the input current, but due to various factors it does not happen, but we want that the output current should be exactly equal to the input current. So, in which case the output current will be more closer to the input current. You can see that since in the denominator there is a 2 by beta square term. So, it means that I reference will be more closer to the I naught, because ultimately what we want I naught upon I reference is equal to 1. So, this quantity 1 upon 1 plus 2 beta 1 upon 1 plus 2 by beta square, it is more closer to 1 in comparison with 1 upon 1 plus 2 by beta, fine. So, the advantage of this current mirror with base current compensation is that the current transfer ratio, it improves in this current mirror. Current transfer ratio, it is better than the basic current mirror, and we are getting it by connecting an additional transistor Q3. So, the main points of this current mirror is the current transfer ratio, we can say that it is less dependent on beta, both are same. If the current transfer ratio is 1, so we can see that I naught upon I reference is it is equal to 1 upon 1 plus 2 by beta square, fine. If the current mirror is independent of beta, then this 2 by beta square term will not be there, then I naught will be equal to I reference. So, you can see that in this current mirror we are getting 1 upon 1 plus 2 by beta square, and for basic current mirror what we are getting 1 upon 2 by beta. So, obviously this one is better, this current mirror with base current compensation is better, because the current transfer ratio is less dependent on beta, fine. And the another point is the output resistance, it is same. Output resistance of this current mirror with base current compensation, it is approximately equal to that of the simple current mirror. So, it means that in terms of output resistance we are not getting any benefit from this current mirror, we are getting the benefit only in terms of the current transfer ratio, because that is lesser dependent on beta. Next current mirror is the Widlar current source. So, to design Widlar current source, what we do? We just connect an additional resistor in the basic current mirror, fine. So, in this circuit if we remove this RE resistor, RE, right, then it will become a basic current mirror, that I had discussed in the last class, fine. So, in the basic current mirror if we connect this resistor RE, that is the, we can say it is a source degeneration resistance, it provides negative feedback, right. So, it becomes the Widlar current source, fine. Now, what is the purpose of connecting this resistor RE? We will see it. By connecting this resistor RE at the emitter of the Q2 transistor, now if we want the smaller current, then we can get the smaller current with smaller values of the resistors. It means that if we are having two current mirrors, one is the basic current mirror, another one is the Widlar current source, and if we want the smaller current, then if we use Widlar current source, then the resistance value required by the Widlar current source, it will be lesser, and that is a good thing, because if the resistance value required is lesser, then the area occupied by the resistor, it will be less. So, the chip area will be lesser, right. So, we can again find out the relation between this output current I naught and I reference. For that we can write the expression of base to emitter voltage for Q1 transistor and similarly for Q2 transistor. The general expression of collector current is IC is equal to IS e to the power VB by VT. Now, from this equation if we calculate the VB1, then we will get VT, obviously there will be ln because there is e to the power VB by VT. Similarly, we can get the value of VB2, that is Vt ln I naught upon Is. So, equation 1, equation 2. Equation 1 is the base to emitter voltage of Q1 transistor, equation 2 is the base to emitter voltage of Q2 transistor, and of course, for Q1 transistor base to emitter voltage it is in terms of I reference, and for Q2 transistor it is in terms of I naught. So, ultimately we have to find out the relation between I naught and I reference. So, what we can do? We can apply the KVL in this loop, right. If we apply the KVL in this loop, then what will be the expression? The expression will be VB1 minus VB2 minus, and if we consider that the base current of Q2 transistor is very less, then in that case the current flowing through the RE resistor is I naught, then we can write it as I naught into RE, that is equal to 0. So, this is the KVL equation in the loop. Now, from equation 1 and equation 2 we can find out the value of VB1 minus VB2, just subtract equation 2 from equation 1 and put this in equation 3. I have marked it equation 3. So, after putting it, what we get? Fine. From equation 1 and 2 we are getting this expression, and this one is we are getting from the KVL equation, and after putting the value of VB1 minus VB2, finally what we are getting? We are getting I naught Re equal to Vt ln I reference upon I naught, where I naught is the output current, I reference is the reference current, Vt is that is the thermal voltage Kt by Q, and at room temperature it is approximately 25 millivolt. Fine. So, this is the expression for Widlar current source. Now, coming to the advantages of Widlar current source. The Widlar current source, as I have already mentioned, that the generation of small constant current, we can do it, we can generate a small current by using relatively small resistors. So, if we are using small resistance values, it means that it will save the chip area, that is the first advantage, and of course, we want to reduce the chip area. Second advantage is the output resistance of this Widlar current source is higher in comparison with basic current mirror. The reason is because we have connected the resistor Re, that is called emitter degeneration resistance, that helps in improving the output resistance. So, these two are the advantages of the Widlar current source over the basic current mirror. Now, coming to the next current mirror, that is the Wilson current mirror. Wilson current mirror. So, Wilson is the name of scientist. Now, in Wilson current mirror, apart from this Q1 and Q2 transistor, there is an additional transistor, that is Q3. Fine. Now, see this Wilson current mirror, we can design it using BJT. Here this is called Wilson MOS mirror, because we have designed this Wilson current mirror using MOSFET. So, Wilson BJT mirror is also there. Now, see what is the use of this Q3 transistor. When we are connecting this Q3 transistor and the gate of this Q3 transistor, it is connected to the drain of Q2 transistor, fine, and this Q1 transistor, it is the diode connected transistor, because in Q1 transistor you can see that the gate and drain are shorted, fine. Now, by doing this connection, we can increase the output resistance by a significant factor. So, the main advantage of the Wilson current mirror is we can increase the output resistance, fine. Now, next one is we are going to derive the expression of the output resistance of this Wilson current mirror. Once we understand that how to calculate the output resistance of this Wilson current mirror, we can do it for other current mirrors also, like Cascode current mirror, fine. So, how we calculate this output resistance? So, we have calculated this output resistance of the amplifier in unit 1, right. So, what we do it? What we do actually? We put input equal to 0. So, here to derive the expression of the output resistance, we will put I reference is equal to 0, and we will connect a voltage source at a node at which we need to calculate the output resistance. For example, the output is taken from the drain of the Q3 transistor. So, at the drain of the Q3 transistor, we want to calculate the resistance, we want to find out the value of the resistance at the drain of the Q3 transistor. So, at the drain of the Q3 transistor, we will connect a voltage source. Let us say the voltage source is Vx, fine, voltage source is Vx, and we will consider that due to this voltage source Vx, suppose that there is a current flowing that is called Ix, fine. So, after doing some network analysis, we can find out the value of Vx upon Ix. So, that is the basic procedure to find out the output resistance of any circuit. What we have to do? at the node at which we want the output resistance, just connect this voltage source and assume that the current flowing due to this voltage source is I x, then just find out the value of V x upon I x, and of course, the input should be 0. So, the same thing we do when we simulate any circuit. If you are using any SPICE tool, any EDA tool, then you follow the same procedure to calculate the output resistance, fine. So, what will be the circuit? This is your Q1 transistor, Q2 transistor and Q3 transistor, fine. Now, just leave this sign of drain current here, ignore this sign right now. Now, see, at the drain of the Q3 transistor, we want to calculate the resistance. So, we have connected this Vx source and due to Vx there is a current Ix. So, we have to ultimately find out the value of Vx upon Ix. RO3 is the output resistance of Q3 transistor, RO1 is the output resistance of Q1 transistor, RO2 is the output resistance of Q2 transistor. Now, see, this is current Ix, fine, and let us say the drain current of Q3 transistor is ID3, then what will be the current flowing through RO3? It will be Ix minus ID3, fine. Now, the voltage across RO1 is, let us say it is a V, right, and the same current Ix will flow through the Q1 transistor also, fine. So, what will be the value of Ix? This Ix, it will be equal to the transconductance of the Q1 transistor into VGS, that is V, because we are considering it V, fine. You can see that this V is the voltage between gate and source, because gate and drain is shorted. So, the same thing, fine. So, we can write Ix is equal to GM1 into V. So, what will be V? V will be Ix by GM1, and what is this V? V is the voltage across RO1, that is in between, you can see that the gate and source, fine. So, ultimately we have to find out the value of Vx upon Ix. So, you can see that Vx is connected between the drain of Q3 and ground. So, ultimately Vx will be equal to the voltage across RO3 plus voltage across RO1, and the voltage across RO1 is V and the V is Ix upon GM1. Now, we have to calculate the voltage across RO3. What will be the voltage across RO3? It will be RO3 resistance into the current flowing through this RO3, that is Ix upon ID3. Now, what is ID3? Now, see, the current flowing through Q1 transistor is Ix and Q1 and Q2 is the current mirror. So, the same current will flow through Q2 transistor, fine. Now, from here you can see that the voltage at the drain terminal of Q2, it is equal to minus of Ix into RO2. You can see that. Let us assume that the voltage at the drain of the Q2 transistor is V1. So, this is the current flowing through RO2, then what will be the current flowing through RO2? It will be 0 minus V1 upon RO2, and what will be the V1? V1 will be minus of Ix into RO2. So, the voltage at the gate terminal of Q3 is minus Ix into RO2, and what is the voltage at the source terminal? That we have find out, right, that is V, fine. So, we know the value of V. So, the point is that what is ID3? Drain current will be the transconductance of Q3 transistor into VGS3. Drain current is equal to transconductance of the transistor into VGS3, and VGS3 is Vg minus Vs of Q3 transistor, and we know the value of the gate voltage of Q3 transistor, that is minus Ix into RO2, and the source voltage of Q3 transistor is V, and V is Ix upon GM1. Just put all these values and just find out the value of Vx, that is the voltage across RO3 resistance plus voltage across RO1 resistance, and just solve it and rearrange the terms, find out the value of Vx upon Ix, that is GM3 RO3 into RO2. Now, you can see that the output resistance, it is increased by the factor GM3 into RO3, GM into R0, that is the gain, and the gain is very high, fine. So, the output resistance of Wilson MOS mirror is very high, because we are getting this factor GM3 into RO3. Now, see, in Wilson MOS mirror, Wilson current mirror, the issue is that the VDS of Q1 and Q2, it is not exactly same. Due to that, there is an error in current transfer ratio, fine. So, to make the VDS, drain to source voltage of Q1 and Q2 equal, we modify this Wilson mirror, and the modified Wilson current mirror, it contains an additional transistor Q4. That Q4 is the diode connected transistor. The role of Q4 is that it makes the VDS of Q1 and Q2 equal. So, this is the modified current mirror to make the current transfer ratio better. Next one is cascode current mirror. So, in cascode current mirror, again there are 4 transistors Q1 to Q4, Q1 and Q4 are the diode connected. This Q4 transistor, it sets the bias voltage of Q3 transistor at the gate of the Q3 transistor, it sets the bias voltage at the gate of the Q3 transistor, fine. So, this is the cascode current mirror, and again by following the same procedure we can calculate the output resistance of this cascode current mirror, that is the at the drain terminal of Q3 transistor. Again we will connect a voltage source and we will find out the value of Vx upon Ix, and after calculation we will get GM3, RO3, RO2. So, we can see that again in cascode current mirror the output resistance is very high, because we are again getting the factor GM3 into RO3. So, the output resistance of Wilson current mirror and cascode current mirror are very high, that is very desirable for any current mirror. So, in this class I have discussed different kinds of current mirror. This is the reference. Thank you.